rationalizing the denominator. Now, what that means is no radical in the denominator. The reason why we do this doesn't seem to be there much anymore. Other than in manipulating formulas, sometimes when in calculus, when I need to manipulate a formula, I need to do that. And actually what we do, and we do it in college algebra as well, is we rationalize the numerator rather than to rationalize the denominator. In other words, we remove the radical from the numerator because it's necessary. So there are some things that you do in terms of dealing with the numerical stuff. Don't need to. Our calculators give us answers in 4 decimal places. It's not necessary to do so anymore. There was a day that you actually didn't need to do this. And a lot of it had to do is if I was going to take 1 and if I was going to divide it by the square root of 3, if I were doing that BC before calculators, if I were to take the square root of 3, square root of 3 is a decimal number. So imagine if you were trying to divide this thing and you were going to do a decimal division, this would be, I would take 1 divided by 1.732050808. That would not be a decimal division you would want to do by hand. Because if you remember what it would be, I need to move this over, is 1.732050808 divided into 1. That's what it says to do. And in the decimal world of division, you move it over. This is 369. Then you'd have 1, 2, 3, 4, 5, 6. I'm running out of paper, 7, 8. I'm really running out of paper, 9. And then this guy would move over there. And then you'd have to do that division. Well, if that's what you had to do, wouldn't you find a better way of doing it so you didn't have to do it that way? You're doing it by hand? I don't need to worry about doing it by hand anymore, because if I now say I want to take 1 and divide it by the square root of 3, there it is. Don't need to worry about it anymore. And it gives it to me to 9 decimal places worth of accuracy. How accurate do you need it to be, right? But BC, before calculators, you needed to get the radical out of the denominator. And that's what the whole idea of rationalizing the denominator was. If you're dealing with a square root, easy peasy, you just multiply it by, in this case, the square root of 3 over the square root of 3. You multiply it by 1. So you change the value, you change the appearance of the fraction without changing the value. Square root of 3 times the square root of 3 is the square root of 9. 1 times the square root of 3 is the square root of 3. It becomes the square root of 3 over 3. Now if you're going to take trigonometry, you're going to certainly run into it there. And now instead of dividing by this horrendous decimal, it says now take 3 divided into 1.732050808. That's reasonable, because you're dividing by a whole number. That's what rationalizing the denominator does. It basically makes the denominator a whole number. Easy peasy, right? Now, if you didn't have a calculator, that's what you would have to, that was what you would want to do. So you wouldn't have to do this division, but you do that one instead. But what do we have? Calculators. So do we care? No. But do we care now? Yes, in the book. I think someday we're going to see that this is going to be a topic like characteristics and mantisses in logarithms that are gone. It'll be gone someday, but just not today. So if I'm doing a square root essentially all I would do is I'd multiply by itself. Square root of 6 times the square root of 6 is the square root of 36. That's now a perfect square. Square root of 30. So it's the square root of 30 over 36, square root of 36, which is 6. And now, looky, no radical in the denominator. Woohoo! That was exciting. No? Okay. Well, you're going to say, well, what if you have something like this? I need this to be a perfect square, so I just anything multiplied by itself is a square. I multiply by 1, just a 1 that changes the appearance, but not the value. Square root of 3x times the square root of 3x is the square root of 9x squared. That's a square. 10 times 3x is the square root of 30x. So what am I going to end up with? I end up with the square root of 30x over the square root of 9x squared is just 3x. And now essentially I no longer have a radical in the denominator. Squares are easy. Easy peasy. Well then, what about something that's not a square? A cube. Cube, fourth, fifth. Here's the concept. If I want a radical to go away and it's a cube root, this radicand needs to be a perfect cube. Now, this is a 2 to the 1 power. A perfect cube would be a 2 to the third. So I'd say to myself, if I have a cube root of 2, what do I need to multiply it by to get 2? And you would say this thing has to be 2 to the 3, right? I'm sorry, 2 to the 2. So that if I had the cube root of 2 to the 1 times the cube root of 2 to the 2, this would be the cube root of 2 to the 3, and the cube root of 2 to the 3 is 2. You need it to be a perfect cube. If I wanted to rationalize the denominator was a fifth root, and I had a 2x squared. That means I am looking for something so that if I have the fifth root of 2 to the 1, x to the 2, I multiply it times something so that I have the fifth root of 2 to the 5, x to the 5. Because the cube root of 2 to the 5, fifth root of 2 to the 5, x to the 5 is 2x. So what does this thing have to be? 2, and I've got 1, 2. How many 2's do I need?
3.
4 to give me 5. I have 1. I need 4 to give me 5. How many x's do I need? 3 to give me 5. So 2 to the 1 times 2 to the 4 is 2 to the 5. X to the 2 times x to the 3 is x to the 5. And the fifth root of 2 to the 5, x to the 5 is 2x. So that when I want to do this problem, square roots are easy. These guys are not. I have a 2 to the 1. I need, because the index is 5, I need a 2 to the 5. So this is going to be 2 to the 4. I need a 2 to x to the 5. So I've got 2 x's. I need 3 more. What I do to the denominator, I must also do to the numerator. So I multiply by 1. Denominator is easy if I've done it correctly. 2 to the 1 times 2 to the 4 is 2 to the 5. X to the 2 times x to the 3 is x to the 5. That's going to kill that denominator. In the numerator, I have 7 times 5th root of 3 times everybody here. So it's going to be 3 times 2 to the 4th. What's 2 to the 4th? 2 to the 4th is 16 times x cubed. Denominator is 2x. The numerator is 7 times the 5th root. 3 times 16 is 48. X 8. My mind moved ahead. X cubed. I know.